Okay. Hey, do you want me to go over uncertainty too? Because that's what we're about to do.
Um, yeah, but I'm on my phone right now. Like, I don't know why I can't join on my computer.
You sent the link to your computer?
No, like I don't know where the link is on Classroom.
If you open up your email,
Okay.
did you let's see. You
Oh.
know what I'll do? I can send you the link on email right now, and then you can do it that way. Copy link address. You know, I'll put it in the stream.
Okay. Yeah, because it was on the text message and then I was looking for it in the
Okay.
stream, but I couldn't find it.
Link for this AM review. Boom. There it is. Period 1, period 9. Post. So hopefully that should pop up for you. All right. So what we're going to do real quick is we're going to go over that sources of uncertainty and how to approach that. So the first thing you should understand is that sources of uncertainty always come from measurements. So there's basically like two rules of thumb here. Hi, Allie. We're talking about sources of uncertainty. Is that all right? We're probably going to take, so basically, we're probably going to talk about sources of uncertainty for like 10 or so minutes. So if you don't need that, you may want to just go do something else and come back in 10 minutes. All right, so sources of uncertainty come from measurements, and they apply to the equations that you use to solve. So this may not seem like it's saying much, but it actually is saying much. So what that means is the following. We first did this. I'll make it red. We first did the school building, the ground, and I'll make the school building purple. And we fired a rocket from the window up here. Here was our window. So we had a rocket shoot off this way. And of course, the rocket followed the curved trajectory, something like this. Ooh. Okay, good. So it landed somewhere over there. We only actually made two measurements here. Really, there are three measurements, but we're going to ignore one of them. We made two measurements here. So measurement number one was this spot. And that actually, we had a tape measure stretched out from here over to here. You could call that the range or the displacement in the x direction. That was something we measured. So anything you measure will have uncertainty. So we measured this to be. What did it come out to? What do you have on yours?
Five.
Was that 41.55? Okay. So, sorry, it's a little laggy. Can you guys hear me okay? Yeah? Okay. So this was 41.55 meters. Okay. Depending on, which class and which half of the class, your number may be a little different. I know one of the classes, we had a kind of a weak rocket. It was like 33 or something, but the process is the same. 41.55. Now, what we talked about in class is that reading this, there was some error in it. There were people standing over here, and they were doing their best to kind of estimate where it hit. But there's no way they could know exactly. There was some range of where it hit. So it might have hit a little bit short of 41.55, and it may have hit a little bit long of 41.55. People were doing their best to kind of estimate where it hit, and we only did it once. So part of our issue is we didn't do enough trials. So we estimated how much uncertainty is there in this measurement. How much do we think we're off? Personally, I think you could be off by as much as 1 to 1.5 meters. But the students who were watching there said, you know what, I think we were close. We were only off by a half meter at most. I said, fine, let's go with your numbers. The point of this right here is to understand the process more than to be perfect at it. So let's say it could have been anywhere from 41.55, half a meter below to half a meter above. And so what you should understand this to mean is, reasonably speaking, the dx is, what's the smallest possible dx? 41.55 minus 0.5.
41.
So, right, so 41, or really if you want to go to the 100th, which is probably silly in this situation, but we'll just do it to keep the numbers. The smallest possible dx is 41.05 meters. And the biggest possible dx, of course, is the plus 0.5. You get your 42.05. Now, the thing about this that hopefully you start to realize is these numbers get plugged into an equation. Now, we plugged in 41.55, but the truth is that may not be right. Anything in between 41.05 and 42.05 could be just as right as 41.55. Because of that, we kind of need to redo the equation and say, well, wait a minute. Though we think it's exactly this number, really it might be a range of possible answers. So let's keep going over here. There's another thing that we measured. You guys, I don't know if you saw me do it, but I did it just because we were rushed. I dropped the tape measure with a weight on it down from the window here to the ground. And we called that the dy. And what I gave you for the dy, I put a little chalk mark up here on the wall, and I tried to line the rocket up with it. And so the dy there was 9.88 meters. Now, was there uncertainty in my measurement? Could I have been off by a little bit? What do you think? By a nod of head, could I have been off by a little bit? Mm-hmm. Even as I did it, I struggled to try to line it up with the chalk, and then you have to look away and try to keep the rocket steady. So there definitely was error here. But we realized, and this is a good realization, I'll put a little comment up here to qualify this comes from measurements business. So the realization is as follows. Let me move this all down a little bit. It comes from measurements, and then you can put a semicolon. Sometimes one uncertainty is more significant than others. So the small uncertainty or uncertainties can be ignored. That's actually a really good thing. Because if you look at every possible piece of uncertainty, it gets crazy. You could say, oh, well, what about the air? What effect could the air have? And then you could say, oh, well, what about the temperature that day? What effect did that have? What about the humidity? What effect did that? And you could keep going and going and going. And honestly, that's why I say you can make this a whole course. The possible sources of uncertainty are in a lot of ways unlimited. Did the fact that the moon, a full moon, the moon was lined up with the earth, does that actually affect the surface gravity on the earth? Well, the answer is yes, a little bit. So there's all this little stuff. And as it turns out, my mismeasurement of the height is actually kind of little stuff. And here's why. We didn't know that the ground was level. We said, a bigger issue is that the ground might have been something like, we thought maybe it was a little higher by the school and that it curved down a little bit by the parking lot. We were up on a curb over here. It's up above the garden. So I dropped down to the dirt in the garden, and they were out actually in the parking lot below the curb. So we said, well, that means that the dy might not really be 9.88. We weren't sure how much it would have changed, and we could have done an experiment to try to figure it out, or a study, but we just decided to estimate that maybe we were off by as much as 30 centimeters, 0.3 meters, or 0.30. So we said, okay, the dy, though we think it's 9.88, really, come over here and write them just like we did before, really dy could be as much as 9.88 plus 0.3, so that makes 10.18 meters. And again, it might be silly to go to the hundredths. It's probably better just to go to the tenths, but this is what we did in class, so we'll keep it going. And it might be as small as 9.88 minus 0.3, which is 9.58 meters. And so here's the thing about this. Once again, we used 9.88 like it was the truth. But it might not have been the truth. The truth could be anywhere, as far as we know, between 9.58 and 10.18. There's even another piece of uncertainty here that might be significant. We're not going to study it this time. We're just going to let it go. But the other one is the angle of this rocket. That's one of those, you want to get a little extra credit, you try to put that in there, but that's a headache. If this were off by even 1 degree, it changes the landing spot. It's not a horizontal projectile anymore. So that angle is another one that we're going to leave alone for this time, because I want you to get the idea how this works. I don't want you to get destroyed by the details. Okay, so that's part one. The uncertainty comes from measurements. The two measurements we actively made were the height, the dy, and the range, the dx. So that's where your uncertainty is. Since those are the only two, we also assume the angle was 0, but let's not worry about that. Now we have to apply the equations. So how do we do this? It's not hard, but it is a little bit messy. Okay, pardon me one quick second. Getting a call that I wouldn't normally get at this moment. Hey, what's up, minute class? Oh, okay, thanks. Okay, bye. Hey! Clara! Tell William doesn't have a delay. Oh. He has to start now. And he needs the glue. Greasy! There's a glue in Lucy's dresser on the top right. You need it. Upstairs? I guess so. It's not down here. Okay, sorry about that. So my kids have a delay this week, or today, sorry, not this week, today. And one of them, because he had a kid in his class that was positive, is on forced quarantine. But apparently he does not have a delay, which means his class starts now. Okay. Complications. Anyway, so let's keep going on this. Now it comes time to solving this business. This is a curved trajectory, so hopefully you know you needed X, Y, R. We didn't end up using the R column on this one, so I'll put it there. We're not going to worry about it. So X, Y, R. And the givens, just to save time, I'm going to throw them in there without units. You know the acceleration, the X is 0. We'll call forward positive. Personally, I recommend calling down positive on this one, because the cliff launch is like a drop problem in the Y direction. All right, so you already did what I'm doing right here. You already submitted this. So acceleration was 9.81 down. And then we knew the VIY was 0. That was 0. And we knew that the DY was 9.88. And we knew that the DX was 41.55. By the way, depending on which group you're with and which class and which A through L, M through Z, your number here may be different. It may not be 41.55. But the process we follow will be exactly the same. And ultimately, what you were trying to find, the goal was to find the VIX. That was our question mark. And so when you did this problem, hopefully what you recognized was the following. And this is a good problem. This is a challenge problem. This is a pump your feet problem. Hopefully what you realized is, well, if I want to get VI in the X direction, since the question mark is there, this is the column you're going to use. And so I need VIX. Well, DAVI, that kind of looks like this equation. D equals VIT. I'm going to put T in a different color because we don't have it. T plus 1/2 AT squared. And this is what I would do first. I would first write an equation that allows me to solve for the thing I want. 1/2 AT squared. Recognizing here that I don't have time and I want it. Okay, so maybe I'll red up this VI over here so we know that's what we're looking for. Hopefully you look at this too and you see that since the acceleration is 0, that this term goes away. You could have also done this with the v bar equals d over t. That would equally work. That would give you the same result because the velocity in the x is constant, so the v bar equation is good. Either way, you need the time. So here's what this is how you approach these problems. Wait a minute. I have an equation that looks pretty good. I don't have the time. Go get it. Where could you get the time? You could get the time from the y column. And so you come down over here and you can do, again, it's actually the same equation, d equals vit, but you're applying it now to the y column, not the x column, plus 1/2 at squared. I'm sorry, I know it's painful to watch me write. It's more painful to do it than for you to watch it, I think. Writing with a trackpad. Okay, anyway. Nice thing here, the vi and the y is 0. So this term goes away. And so this actually gets down to what you did. You solved for time. And so if we rearrange this thing, which is a good habit right here, I'm going to rearrange it for you. Time is going to equal, multiply both sides by 2, so you get 2d. Divide both sides by a, so you got 2d over a. And then you got to square root both sides because it's squared. So square root 2d over a. Okay, cool. Once we get this time, we then can bring it over here. Now, I didn't discuss this in class because when you discuss this in front of 20 people, it usually gets lost. But since it's just a few of us, I'm going to show you a neat little trick here. Doing this with letters first saves you because now I can come down here and write one equation. Here's the equation that will cover the whole thing. D equals VI, which we're trying to find, times, we don't have to put the letter T in there anymore. What could we put in there instead? You could put what T is equal to, right? T is square root of 2D over A. Square root of 2. Now, just so we make sure we're not confusing this is D in the Y direction over A in the Y direction. And this will actually save you a little time. This is D in the X, and this is VI in the X, which we're trying to find. So, of course, we're trying to find VIX, so I would just rearrange this. VI in the X is D in the X over this whole thing, you divide both sides, square root 2dy over ay. All right, now I know this is the sort of thing that if you zone out for a second and you zone back in, you're like, whoa, what just happened? So is anyone experiencing that moment right now? If you are, please speak up. It's okay if you are. I remember that moment probably hundreds, if not thousands of times in college. So it's not a strange thing for you to experience that. Are you okay with this line? Because I don't want us to keep going here unless you feel okay with what's written right here. Speak up if there's an issue.
I'm just like, is that the equation you're using to find VI before in like part 2?
This is, yes, that's exactly right.
Okay, so we're not on uncertainty right now.
Well, we're going to use this to find the uncertainty. So basically what I did right here, you already did. You did this, and what you already did, I'll put it over here, already done. And you'll see why, though, I'm forcing you to think about this again. What you already did was, you probably did it separately. You probably did this term right here, t equals square root 2d over a, right? So you did this, and you got, let me see what you got. You got square root 2 times 9.88 over 9.81. And so 9.88 and 9.81 are almost the same thing. And so this probably comes out to a little bigger than 1.4. What'd you get? 1.4 something. Right?
Oh, wait. Sorry, I didn't mean to do that. But like I didn't use that. I don't think like we used that formula.
No, you did. You just did. You probably did this one. You definitely used this formula. You
So did
probably
you just rewrite it?
you
Rewrite
plugged it into this one.
Yeah.
So on your paper, I'm willing to bet that it says 9.88 equals 0 times t plus 1 half 9.81 times t squared.
Yeah.
So when you do that math, I just rearranged it first.
Oh, okay.
So what'd you get? You got 1.4 something, right?
1.42.
Okay, 1.42. So you already did this. What I'm telling you, you're going to have to do now. You don't have to make the whole chart again. There's no reason to make the whole chart again. What you have to do is redo the substitution, the plug-in. Except now, you're going to plug it in with, you're actually substituting based on this comment right here. You see this? You plugged in 9.88 the first time. Now I want you to do it twice more. Don't make the whole chart again. Just come over to this equation, and right here where it says D, you're going to do it once with 10.18, and then another time with 9.58. So you will have done this equation right here 3 total times. One time with 9.88 that you're already done. A second time with 10.18, and a third time with 9.58. Is that a little bit annoying? Yeah. Is it a lot of bit annoying? It's not that bad. This lab's worth almost as much as a quiz, so it's going to take a little work.
Do we need to do can we just do the regular formula, like not rewrite it?
Yeah, you mean like this here where I circled in black?
Yeah.
Absolutely. So I'm going to show you why I did this black one down here in just a second. So if you want to do this with what's called the brute force method, the brute force method is less trickery of thinking, but more writing. So if that's the way you want to work this, it's fine. It works. It's going to take you a little longer, but it's fine. Not a lot longer. So you're going to do this twice. Once with 10.18 and once with 9.58. And you're going to get 2 different answers. Did anybody do this yet? I mean, you might as well try it as we're sitting here. See what you get is your times. You're going to get 2 different times. So originally we got 9.42, but now we're going to get one that's less than that, and we're going to get one that's more than that. So I'm going to put a little dividing space here. The left side is going to be what we call the finesse method. Finesse method is if you're feeling comfortable and it saves you ink. The right side is what we call the brute force method. The brute force method is more straightforward, but you got to spend more ink on it. You got to do more writing. So I'm okay with you doing either one. Doesn't matter. So you should now have 3 times the 1.42 that you originally did, and then 2 others. You could take a second and do those. See what you come up with. And of course, you want to write this all on the paper. Don't just come up with an answer and leave it there. And write it without any work. I'm going to run it in my calculator too right now. Let's see. 2 times 10.8. So I got 1.44 for one of mine. And so you should, check the same thing, make sure you do also.
Wait, when you plugged in 10.18, what did you get?
I got 1.44.
I didn't get that.
What did you get?
2.07.
Yeah, but you got to square root both sides. It's t
Oh,
squared.
yeah. I forgot the square.
Yeah, that's all. And the other one, I got rounds to 1.40. Agreed? Okay, so if you got at least one of them, then you're going to get the other one. All right, we agreement? Yeah? Okay, good. So you're part of the way there, which is nice. So this 1.42 is already done. And the new ones here are 1.44 and 1.40. So when you said the time this took to hit the ground was 1.42, you were not justified in saying that is the answer. What you're really justified in saying is that the time is somewhere between, we use that bracket notation from math. The time is somewhere between 1.40 and 1.44 seconds. That's really what this is saying. Now, we're going to use this time when we plug into the next part of our equation. So we can't just say, oh, time's automatically 1.42. No, time has a little range of possibility based on the uncertainty. All right, so I'm going to skip over this little finesse piece for a second. And I'm going to continue us on brute force because I think I'm getting the sense you like that one a little better. I'll come back to the finesse in a minute. But now that we have the time, remember the whole purpose of getting the time was to be able to come back over here and answer this. D equals VIT. So let's come back over here. We're going to continue our brute force down here. So the whole purpose for us getting the time was so that we can answer this question. D equals VIT for the X column. You remember doing this? You guys see why we're going back to this now? Because ultimately our goal was VI. So if you want to rearrange this, it's actually pretty easy to rearrange. VI equals D over T. Now here's what you already did. What you already did was you already plugged in D in the X, 41.55. Just remember, your number might have been a little different. You might have been 40.92. You might have been, one of the groups was 33. It's whatever distance you got here. 41.55 over. But you, by the way, if you're watching this and you're not sure what, you can use the 41.55. I don't care. Over what you already put down here was 1.42. You already did this. And so you already got, by the way, let me ask the people in here, did you all use 41.55 or did you use a different number? All right, so you already got something like 29.3. Somewhere in that vicinity. If you had slightly different numbers, you can get a slightly different answer. You already got 29.3. Are we in agreement? Yeah? If not, speak up because it's an easy thing to clarify. Okay, so we already got 29.3, but that was assuming that our dx was exactly 41.55 and that our time was exactly 1.42. So now this is where you have to run that uncertainty. Now, is distance definitely 41.55? Yes or no? No. What we saw up here is that the distance is anywhere between 41.05 and 42.05. So I'm going to put a little a little range up here. 41.05 to 42.05. The distance is anywhere in that range. Then is the time automatically 1.42? Well, no. We just discovered that the time was anything between 1.40 and 1.44.
Did we find that out substituting 9.80 with plus or minus 0.3 meters?
Yes, this 1.40 to 1.44?
Yes.
Yes, absolutely. You see up here, that's what I said. The plus or minus 0.3 is this 10.18 and the 9.58. You remember that? Which came from what we said up here, the 9.88 plus or minus 0.3, 10.18, 9.58.
Okay.
Okay? So from that, so think about this. From the uncertainty in dy, we ended up with an uncertainty in time. Now when we try to get the vi, we have an uncertainty in dx and an uncertainty in time. So just like you did before, you're going to have to do this d over t twice. Only twice. Don't do it 4 times. Only twice. And so here's the challenge. What numbers will you use? And the key to understanding this is you want to use the numbers that will give you both the biggest VI and then the numbers that will give you the smallest VI. So which 2 numbers are you going to use to get the biggest VI? Remember, you got 2 choices up here for D and 2 choices for T. So what combination, what D and what T are you going to use to get you the biggest VI? Go ahead.
Wouldn't you use a 42.5 and the 1.40?
Yes, exactly correct. So if you use, here, let's do a solid underline. If you use 42.05 with 1.40, you will get the maximum possible VI. Do it. See what you get.
Bye-bye.
Have a good day at school. Make sure you learn something. What are you going to learn? Okay.
Walk. We're gonna walk.
You going to learn walk?
No, walk.
Rock. That's good. It's good to learn. See, earth science. There it is. So do those 2. You do the max numerator with the min denominator. What do you get? I'm going to try it also. I got 30.0 basically. You guys agree? Nods of agreement, disagreement? Yeah? That's the maximum possible VI we can have because we took the biggest D with the smallest T. Now let's switch this around. If we want the minimum possible, of course you would take the smallest displacement with the biggest time and do the equation once more. And if you do that one, I'm getting 28.5 meters per second.
Wait, why are there 2 numbers on the right? 29.3 and then it's pointing to 30.0.
29.3 is what you originally got. Yes?
Okay.
So that one you already did. The point of this
Oh.
second piece of the lab is to say, now wait a minute. 29.3, though we act like it's the exact truth, we are not justified in saying that. In a sense, we're lying.
Yeah.
So how can we less lie? How can we tell more truth? We have to say, well, wait a minute. This 41.55, it might not be 41.55. It might actually be as small as 41.05, and it might be as big as 42.05.
So you got the 30.0 with the bigger
Right.
41.
So you realize you could make all the combinations you want here, but the biggest possible VI you're going to get is going to be when dx is as big as possible and t is as small as possible. So that's why we said, let's match the 42 with the 1.40, and you end up getting 30. Make sense?
Yeah, that makes sense.
Alternately, we want to find what's the smallest possible VI we can get. So we matched our smallest dx, 41, with our biggest time, 1.44, and we got 28.5. So the net effect of all this slop that we just did over here, here's the net effect. Net effect. The VI of the rocket, which was our whole goal for part 2, is anywhere in the range from 28.5 to 30.0 meters per second. That's the whole net effect of this business. That's why we did this. That's for part 2. Part 2 net effect. Now, to throw it back to the finesse method, just in case anybody watches this or in case any of you are interested, since over here I made one equation, VIX is dx over that square root term, you could have plugged all the uncertainty into here in this one equation and it would have been done at once. So I would have put for dx, I would have put the 41.05 to 42.05 up here in the numerator, and the dy I would have put the 9.58 to the 10.18. Would have done this one twice and would have gotten the same range. It's the same thing, you know, like they say, 6 of one, half dozen the other. Whatever makes you comfortable, it'll work. All right, so that's part 2. We have to go back to part 1 now. We have to use this. Now, part 1, fortunately, is a lot easier. Part 1 was just the vertical launch. Part 1, we had the ground, we had the rocket, and the rocket did this. I mean, our rocket actually drifted a little. We didn't want it to drift. We wanted it to go straight up and come straight down. As it turned out, it did drift a little bit. So, you know, it's okay if you draw it like that. But basically, that's what our rocket did. There's a little rocket down there. Because it's a vertical launch, do you need a chart? No need for a chart. I mean, you want to put a chart and only fill in the Y column, that's fine, but you don't need a chart. What we know here about this one, and this is what you did already, your goal for the vertical launch was to figure out the time, the total time. Total time was our question mark. That's what we needed to figure out. What did we know for certain? Well, usually for the throw up, this is the vertical launch, the up version, not the down version, obviously. Usually for a throw up problem, I tell you to use up as positive. So we know the acceleration. What is it? I don't know that acceleration. If up is positive, what's the acceleration going to be?
Negative 9.81.
There you go. So negative 9.81 meter per second squared. All right. And then we know the VI. Now, originally, what you wrote over here for VI, you wrote 29.3, or whatever you got the first time you did this. You wrote 29.3. However, what we have discovered up here is that this could actually be as low as 28.5 or as high as 30.0. Hello. So that's our range of VIs. And just like we did before, we're going to have to shove them in here. There's one more given needed. What given do you want to use? There's a few different givens you could use to solve this, by the way. I might as well write them all down so you're comfortable with them. There's a few different givens here. Because this comes back to the ground, so I'm going to put a little dashed line here. More than one way to skin this cat. You can use whatever given you want.
Get something.
You got school, fool. Get to it.
I need to get something.
Okay.
My problem of the day. I have no more pages in it.
What is the D at the end? What is the D at the end? That's one given you could use to get this. What's the total displacement? This is a nice given. Maybe I'll put this on the quiz Friday real quick. Just boom, what's D at the end? And hopefully you don't do any math for it. You just know the answer.
0.
Yeah, it comes back to ground level. You could use that given. Did anybody use VF peak? Did anybody do it that way? Okay, some of you will do this as VF peak. And of course, VF peak is 0. Can you hear the footsteps in the video? That's my oldest. She's crazy.
I have a question.
What?
How come D is 0 here, and then before, when we were doing D, it was 9.88?
That problem, have a look. You got to understand what the letter D means. D is displacement.
Yeah.
Displacement means, here's a little aside for us. I'll put it over here. Displacement is always, by definition, the shortcut from start to finish. So displacement is basically circle the start, X the finish. For this problem, displacement in the Y direction. In the Y direction, it started out up here. Agreed? In the Y direction, it ended on ground level, which is down here. Agreed? This is the vertical displacement.
Oh, okay.
On
So,
the throw up problem, it started on the ground.
Yeah.
Where did it end up?
on the ground.
On the ground. So in the Y direction, how much displacement is there in the end?
0.
0. That's right.
So when you say in the end, doesn't that mean like resultant, like the whole thing?
It could, for this vertical problem, remember that you don't need a chart for a vertical only problem.
Yeah.
But yes, that's exactly what that means.
Okay.
And the resultant displacement, if this were truly vertical, it would have landed right where it started. There was wind, so it drifted over like here somewhere. So it didn't really have 0 displacement. It had this X displacement. But if you want to make a column for this one and say, oh, look, it went on an angle. I want to make a chart. That's fine. You're still going to figure out the time with the Y column. And in the Y column, the displacement at the end is 0. Okay? So you could have used VF peak. But what's our issue here? If you use VF peak as 0, what do you have to do?
Times it by 2.
Yeah. So you need to times your answer by 2. Don't times like in the middle of the problem. Whatever your answer comes out to, times 2. There's even another way to do this. You could have said VF at the end, and yes, this would work. You may not like this, but if you're thinking about going to AP, you need to start to like this. VF at the end is equal to negative VI, which in this case would have been negative 29.3. So this would work as well. I don't care what method you used. What was your original, what equation did you use? We got a bunch of choices here. Who used VF peak equals 0? Raise your hand. Okay. Then, what else did you use if not that? I'll write that one over here. So some of you use this one. You did VF at the peak equals VI plus AT. You plugged in your numbers, right? If I were to rearrange this thing, I would rearrange it because I'm trying to find time. I would rearrange to be time equals VF peak minus VI over A. And of course, this gives you the time to the peak. This does not give you the time to the end. And so when you plug this in, what did you get? Well, you had 0 minus 29.3 over 9.81, except 9.81 was negative, so this should come out positive. It does. Okay, so this is what you did the first time, yes? Yeah? You should have got somewhere around 3 seconds. Does it come out to exactly? 29.3 divided by 9.81. You should have gotten 2.99 seconds. If you go to 2 sig figs, you'd call it 3.0 seconds. If these were your numbers. If your numbers were a little different, then fine. And of course, you then have to times 2. So your answer was 6.0 seconds. That's what you did the first time. You already did what I have written in black here. Now, you're going to do this again, except instead of popping in 29.3, we have a range. We have 28.5 to 30.0. So, how many times you got to do this plug-in now? 2 more. Peace. Deuces. Yes. So do it and see what you get. Because you will not get exactly 3.0. You're going to get something, depending on which number you use, you're going to get something a little less and something a little more. I'm going to try this out right here. I got 2.9. I'll carry one extra sig fig right now. My low end, I got 2.91. And my high end, I got 3.06. You guys getting those two? And then if you double those, because that was just to the peak, 3.06 times 2, of course, is going to be 6.12. And then 2.91 times 2 is going to give you 5.82. So the result of part one net effect. The T total will be in the range of 5.8 to 6.1. 5.8 to 6.1 seconds. If you went to the 100th, 5.82, 6, I don't care. That's fine. We're not sweating the sig figs on this one. This is more about approach to uncertainty. Part one, net effect. All right. Are we all good on this one? Everybody with me on this one? We feel comfortable with it? Final comparison. You ready for the final comparison? It's the final countdown. Do-do-do-do. I know you heard that those basketball games. Okay, so final comparison. We need to compare it to video. Compare to video of vertical launch. And here's what we found. We only watched one video. The video we watched was with one of Cole's videos pumping the thing. And what we found from his video, T video, was 5.87 seconds. That's what we came up with. And this too had an uncertainty of, we went over this and we said it was like, we thought it could have been off by as much as 1.5 frames. Partly because we just missed, the beginning was hard to get, and also the,
Dad, I'm going to school.
all right, have a nice day.
All right, bye.
You better keep that shirt closed.
Bye, Dad.
5.87 plus or minus 1.5 frames. Now this we have to turn into time. We can do that right here. 1.5 frames. The frame rate of the camera was 60. 60 frames, 1 second. And so what does that come out to? 1.5 divided 60. Actually, you could get that one in your head. What's 15 divided 60? That's 1/4, right? 15 over 60 would be 0.25. So 1.5 is 0.025 seconds. So really this was 5.87 plus or minus 0.025. So we can write this now as a range. That's really the way you want to do this ultimately. So T vid equals, what's the range? What's the smallest it could be? 5.87 minus 0.025. What's that, 5.84 if you round it? Yeah? And then if you go up, it's 5.90 seconds. And so here is actually where you make your comment that basically says, hey, there was purpose to doing all this junk. Here it is. Is our calculated answer, or does our calculated answer get verified by the video? That's a yes or no question. Our calculated answer is it's somewhere between 5.8 and 6.1 seconds. The video tells us it's somewhere between 5.84 and 5.90 seconds. Are we justified? Yes or no? What do you think? Somebody say it out. Yes or no? Yes.
Yes.
Yes, we are. Yes, we are. Yes. The video, which we're taking as like the truth, says it's somewhere basically between 5.8 and 5.9 seconds. And our calculation, that fits within our calculation. Our calculation says our answer is somewhere between 5.8 and 6.1, which means the actual answer fits inside of our range of uncertainty. That's really that's what you call a positive result. When the actual fits inside your range, you've verified with that experiment. So this actually is this actually worked out real well. I did not know ahead of time whether this would work, but based on what we did, it did. Hold on one second. Hello? Hello? Yes. No, William has school. I don't know about Lucy. I don't know. I guess if they're not there, come on back. I didn't see. Let me check again. Hold on. I don't know. I don't see anything. I guess just come home. All right. Bye. Wait. Managing remote or what do you call it? Delays. Nonsense. So this is a pretty cool thing. I mean, I don't know if you feel fulfilled by the process, but it's a pretty cool process that this actually worked out. This, by the way, helps you recognize, though, that like if our range up here were anywhere from like 2 seconds to 10 seconds, you would be like, well, who cares? The fact that our range is actually pretty tight and the actual fits within it, that means we did a pretty good experiment, pretty good measurements, pretty good conditions. So there it is. That's why this lab is worth points, because that whole process of what we just did there, that takes time and it takes thought. All right. Whew. After all that, anything else?
So if we have now the so if we had the sources of error, percent error, range of uncertainty, then we're good, right?
Yes. Yeah, this is the last bit of it.
I put down percent certainty, but
That's fine. Yeah, I'm not so worried about the term. We didn't technically express this as a percent. That's why it's not technically a percent uncertainty. We could have, though. We could have made it a percent. You know, take 6 as the, and then you would do a plus or minus whatever percent it is. But you know, just a range of uncertainty is fine. It's easier than worrying about a percent. So that's that. Wait,
so do we have to use like a certain like number to find like a percent error or like that?
Yeah, the percent error you actually did before we did all this. I don't care if you do it after. The percent error was take the time that you originally came up with, 6.0 seconds here, and take the time. So percent error is based on what we think our best approximation is. So we say our best approximation is it took 6 seconds, and our best approximation is the video was 5.87 seconds. And so based on those two, you do your percent error. So you remember you do measured minus actual over actual times 100. So you'll do 6 minus 5.87, whole thing over 5.87 times 100, you get a percent. So you're off by a little bit, but the only way you know whether that amount you're off is okay, in the past they told you something like, oh, if you're less than 5% error, that's good. Or, oh, if you're less than 10% error, that's good. But that's kind of make-believe. Really, the actual way to do it is you look at your percent and then you say, well, wait a minute. Does my range of uncertainty or my percent uncertainty, is it bigger than my percent error? Is it equal to or bigger than my percent error? So your percent error was, let's see, percent error came out to, let's see, it was 5.8, no, the other way around. 6 minus 5.87, which is 0.13. 0.13 over 5.87 times 100. What'd that come out to? Anybody calculate that yet?
It's like 2%.
All right. 2 point what? Give it one decimal.
2.2.
Okay. 2.2% error. Fine. The percent uncertainty, you know, if you really wanted to compare percents, I didn't want to add an extra step, but you guys sitting here, you can do this. It's fine. Percent uncertainty is basically how much is this off from this. And you got to do it on both ends. So you can say 5.8 compared to 6. So you can look at it, you know, look at it from the low end and the high end. You could say 0.2. Do the same thing like you're doing percent error, but you just do it with the 5.8 and the 6. So the percent uncertainty in your time is 0.2 over 6 times 100, which, by the way, is going to be bigger than this number. You can tell already it's going to be bigger than this number. That's going to come out to like 3%, right? 3.3%. Anybody? Anybody? So basically, you can look at this. You can also do the high end, the 0.1 over it, and it comes out to like, I don't know, 1.7%, something like that. But your percent uncertainty here, this number is bigger than this number, and so you're good. Again, I didn't want you really to worry about
Wait,
this.
but where'd you get
Where'd I get the what?
the 0.2?
I did
for
5.8.
7% error.
Wait, for percent error, percent uncertainty. The 0.2.
Uncertainty.
Yeah, that's why I didn't actually put this as part of your assignment. I didn't really want you to worry about a whole nother level of percents. It's like already what you had to worry about was a lot. But you would look at what your smallest, look at your range. The smallest you could allow is 5.8, whereas you think the best answer is 6. So you basically do a percent error calculation from your smallest to what you think your best is. That's 5.8 minus 6 is 0.2. Well, negative 0.2. That's where the 0.2 came from. I'm going to put a line through this. You do not need to worry about this. That's once you get comfortable with this process, you can go to percents, but you don't need to worry about it. What you need to worry about is, does the actual fit within our range? And if that's the case, you did good. As the experiment worked. Sorry, you did good is the wrong way to put it. The experiment worked. Another way to compare these things, which we can do later on, or I don't know if we'll do this year at all, is you literally take the thing you're used to doing, percent error, and you also calculate something called percent uncertainty, which you can do by comparing this to this, and you see which is bigger. If percent error is bigger than percent uncertainty, then you can't trust your results. If percent uncertainty is bigger than your percent error, then you can trust your results. That's like a loose way to look at it. So that whole thing where they taught you back in the day, like, oh, you got to be better than 5% error, 3% error. Like I said, that's like a make-believe thing. It's almost like when you started graphing, you thought everything went through the origin. Like, yeah, a lot of things go through the origin, but not everything does. So yeah, 5% error is like good for some things, but it's not good for everything. The real way to do it is to compare percent error and percent uncertainty. And we'll see, depending on how people do with this and on how much time we have, and this obviously takes a long time to do, maybe I'll teach you percent uncertainty a little later in the year. But you've done all the hard part. This is just like an extra piece of complication that we'll see. We'll see how people do on it. All right. That's it. No more on that, unless you got a question.